Welcome everyone to our second episode of Hexagonal Architecture, also known as ports and adapters. So here are some general links which might be useful for you for further reading. And now we'll get onto it. So let's see where we left off from last time. So I'm sharing the diagram where we arrived from our previous session. So essentially, we looked at the presentation layer, so the driver adapters, the driver ports, the business logic, the driven ports, and the driven adapters. And the most important conclusion that we came to regarding hexagonal architecture is this, dependency inversion. The fact that we have interfaces for the driver ports and the driven ports to decouple the business logic, to decouple it from the external world. So this, we're going to continue on with this diagram, and we want to transform it visually so that we can recognize it as the official, hexagonal architecture diagram. And the other also thing that we will be doing is looking at even further adapters here and additional adapters here as we increase business requirements and need to perform additional operations. And depending on time, we may also discuss some controversial topics about databases. We'll see if we get to it during this session or next session. But anyway, I'm now going to continue on. So yeah, zooming in, and I'm going to, let's see. Okay, great. We can see it. And I'm going to copy paste this below. And let's start our transformation. This is just a visual transformation to make it look like Alistair Cockburn's diagram. So what we're going to want to do is this presentation, the driver adapters, we want to move it onto the left-hand side, and this we want, the driven adapters, we want to move it onto the right-hand side. So I'm just going to extend this so that I have a bit more space on the left and the right. And for now, I'm just going to remove some of these labels. We will stick them in later, but I just want to avoid distractions right now. So let's see. So I'm moving all of this stuff to the left-hand side. And so I'm just moving the adapters, and I'm moving these driven adapters to the right-hand side. And then for the driver adapters, I'm just going to change the arrows because of this movement to the left. I'm gonna put all of this here and this connecting here like this. And we're doing this step by step because this is the part which many people do find confusing about hexagonal architecture, the diagram which appears on the actual website. So let me just change this to be here. And then this might be useful later when you share it with any of your colleagues who want to see, how we get from traditional architecture to hexagonal architecture. So there we go. We've moved that part, and let's move this other adapter. Okay, so this has gone to the side. Okay, great. And we also have the tests. Okay, so that's one way. We've moved the driver side to the right-hand side. And we also would like, when you look at Alistair Cockburn's also website, you will see that the ports themselves are also, left-hand side and right-hand side. So I'm just going to adjust that as well. So there we go. This is our left-hand side, which is that whole driver side. And these are the adapters and these are the ports. Let's now move on to the driven part. So the driven adapters, okay, let me see. Okay, I'm just going to redraw that line. And let us move all of these here. And again, I'm just going to reconnect. So we're doing all of this step by step so that we can see exactly, how we're going to get to the hexagonal architecture official drawing. And just visually, let's do this. So again, connecting it to the left, connecting this to the left, moving it up. Okay. This part again to the left, and let's see this part to the left, and let's change the connectors here. So, okay, well, nearly there. Okay. We have now drawn our driven side. And this diagram that you see now, this is already resembling the official diagram. And okay, these parts are the driver adapters. These are the driver ports. And similarly, we have, these are the ports. And these are the adapters. And then I'm just going to switch over to Alistair's diagram to see if there's anything else that we want to draw on here. So I'm just going to go and switch to Alistair Cockburn's diagram. So here we go. We have the hexagon, we have the left-hand side, and we have the right-hand side. So that's exactly what we've drawn here. And let me just switch. The other thing that we can see is that instead of using a rectangle, I mean, this was a completely arbitrary choice to use a rectangle. Let's use a hexagon instead, which was also a completely arbitrary choice, but just that it looks more like the official drawing. So we're going to use a hexagon. And I'm going to delete the rectangle. And you will also see in his diagram that he has also a second, that he has like an inner hexagon, but then let me see. But that we also have, you see, the inner hexagon and the outer hexagon. So I'm going to update our diagram so that we also have the inner and the outer hexagon, which is the one that's going to include the adapters. So I'm just going to give myself some space here. So let's see how this outer one, okay, this is a bit of a challenge in terms of drawing. It's not so easy to fit stuff. So I'm just moving stuff around, and let me put the adapters. So he's putting the adapters here. Okay, maybe a bit more space. Okay, this is now starting to look really like the official diagram. And let's put these ones inside here. There we go. The adapters are in this outer hexagon, and then the actual, physical databases, notice how they are fully outside. And similarly here, all of these, any other external actors like people, scripts, etc., who are using adapters are completely outside. And just bringing back, okay, that's the driver side. These are the ports. These are the ports. These are the adapters. These are the adapters, and that's pretty much it. Here we've actually reached the diagram that appears in Alistair Cockburn's and any other, material that you see about hexagonal architecture. So I'll just switch over and look at, okay, thanks everyone for all the comments. So feel free to write anything here in chat if you have any comments or questions. So now I hope that with this, you've seen how we've actually derived the hexagonal architecture diagram. And what we're going to be doing now is a bit of additional generalization. Let's see. Okay, a question. Are the ports and adapters merely interfaces, or could they contain a functionality, mechanism, or algorithm? Okay, I like that question. This is the part where we are supposed to, in the business logic, this is where we should have, I guess, the primary functionality of our application, like implementing the requirements, such as here, we want to make, let's say, submit an order. So in the business logic, we want to check, do the products exist? What are the product prices? Calculate the order price and tell the port to save the order. So that's the kind of functionality which belongs here in the business logic. Coming back to the next one, mechanism or algorithm. Similarly, generally algorithms, you would put algorithms here inside the business logic. So you may have a certain algorithm for calculating the order price, which could include summing the products, multiplying by quantities, calculating shipping costs by multiplying by some coefficient. So that's an example of a business logic algorithm, if that's what the question is referring to. So that's the kind of stuff which is in business logic, so inside this hexagon. These adapters are supposed to be as thin as possible. So I just want to emphasize that this is like this internal hexagon, this is our focus. Business logic is here. This is actually essentially implementing business requirements. And this part we wanted to be fat. Like this is where we expect to have a lot of code and a lot of complexity. Our adapters are supposed to be thin. So these essentially here are, for example, HTTP wrappers. So a REST API is just a HTTP wrapper or some UI representation, but they are supposed to be very thin. And these other adapters for the database, these should just be database, for example, CRUD operations, but they should not contain, for example, logic how to calculate the order price or things like that. So they should be, relatively thin. So this is fat, and these adapters should be thin. Like this is the most interesting part of our application. Adding to the question, what is the implementation of the port? So here, for these driven ports, the implementation of these interfaces is in the adapters. So these are the adapters, and that's where we implement the actual ports. Oh, and this is the other part which may be sometimes confusing about hexagonal architecture. This relationship here is an implements relationship. Maybe I should extend this because now the text isn't really readable. 1 second. Regarding this question about implements. Okay. So these adapters, they implement the interface. So if we could, read right to left, that's the implementation, that's the interface. So this is an implements relationship. Whereas for the actual test runner, I would say that it uses the interface. Whereas here on this other side, it is not an implements relationship. So I can't say that the REST API implements the order API, but rather that it uses. Currently, this maybe sounds a bit too abstract. Maybe later we could have examples to illustrate or something when we get to the details. Okay, can you tell more about the project structure? How do you prefer to place your interfaces and implementations for the hexagonal architecture? Okay, I'm going to put that as a to-do point to discuss architecture layering, because that is actually not defined precisely. So hexagonal architecture defines just this conceptual separation, but there is no specification of layering. So what I'm going to show after we do some other things are examples of concrete layering. Where do we separate the concerns that commands that mutate state versus queries? Okay, alongside with that architecture discussion, we can discuss commands versus queries for they belong to the user side ports. Okay, great. So excellent questions. I think I might get to these ones actually during this session, after I firstly do one more thing that I wanted to do. Now, notice here how we have just one port and just one port. In reality, I do want to emphasize that there are multiple ports. There can be, multiple ports and not just one port like I've drawn here. What I'd like to now go into is a more generalized image, which has much more ports and much more adapters, just so that you can get the bigger picture. And then after we do that, I would like to come to these questions that were asked about architecture and how we could do some layering. Okay, now this diagram is very big. I'm not sure. Let's see how understandable it's going to be. Maybe I'll introduce some just background coloring, that this is well, I drew a rectangle, but let's just say it's the hexagon. Okay, just if you could imagine if that's a hexagon. Let's look at examples of driver ports. So driver ports, they represent use cases. Let's say we have a driver port order service interface. which could have methods like submit order, cancel order, get order details. So the stuff that's needed by some users. Let's look at possible adapters that could use that service. So we can have tests which are targeting that service to test, submitting order, canceling order. We could have REST API controllers, and then within dependency injection, you'd inject the order service. We could have a SOAP API, a GraphQL API, gRPC API, WebSockets API. Notice that all of these are just, different ways of formatting, different ways of providing input and output to the external world, like whether it's, JSON or XML or some other format. But the essential logic, the use cases remain the same. So we're still talking about submit order, cancel order, view order details. So notice this essential thing, that we can run tests. So some test scripts can directly run on the order service interface without knowing anything about the UI. So these tests are pure, essentially, business logic tests. So I just wanted to emphasize that. Then when we have the REST API, sure, you could have, SPA application. So you could have a React application, a desktop application, mobile application, MVC application, command line interface application. You could even have an FTP server if you need to provide something to other legacy systems. And then we have the actual actors. So the REST API, it's, as I said, it could be used by SPA apps, desktop apps, whatever, but it could be used by any other external system. So maybe for another team or another company wants to connect to us, so they can, call the REST API. Notice that we have the test appearing here again. I just want to distinguish between this test, which is testing the driver port. That's the test which is, those test scripts are purely business logic tests. Whereas these other tests are presentation layer tests. So a test which, some tests which are executing the REST API because they want to verify, do the endpoints, can we properly connect to the endpoints, can we pass JSON in and JSON out? And the UI, they would have their own tests. So I just want to distinguish again between business logic tests, which are connecting to the driver port, versus presentation layer tests, which are connecting to presentation mechanisms like, the REST API and the rest. And then we ultimately have the people as well who are, for example, using the UI. Okay. So let's see. I'm a bit confused. Why REST uses port instead of implemented? Okay, I like that question. It's a common one. I think I could put it as a to do here when we get to architecture. So REST API using services. That's the part where I want to talk about dependency injection, how we inject a service into the REST API. So that's why it's a users. Now I have a question. Do we have to stick with REST APIs or SOAP APIs? All of this is providing synchronous communication with something. So for example, some other systems could connect to us via REST API or SOAP API. But what if we wanted fully asynchronous event-based communication? Well, then maybe we don't want to expose REST APIs. maybe we want to use RabbitMQ consumers or Kafka consumers, or maybe we want to use both. So this is really quite something interesting that maybe not everyone is familiar with, but RabbitMQ consumer and Kafka consumer are also essentially the presentation layer to our backend. And once again, we would be injecting the order service interface into the RabbitMQ consumer class and into the Kafka consumer class so that they can call the ports. So just to distinguish between REST API versus the consumers. In the REST API, you may have a controller which is called order controller, and it has methods like, submit order, and it takes some JSON, and it simply delegates to the order service, dot submit order method. So this pretty much does nothing aside from just delegating. These consumers will do pretty much the same thing. So if the Rabbit consumer maybe received some event, and in response to that event, it needs to trigger, the submit order, then within the RabbitMQ consumer, since we've injected the order service interface, we would then say order service dot submit order. So same thing as what the REST API is doing. And again, these would be really, really thin. They would have not much code. Okay, and this comment, the API is a facade to the system. So since the word API is overloaded, I just do want to emphasize that we've spoken about REST API, SOAP API. This thing here, it's actually also called an API in Hexagonal Architecture. This is called the user-side API, not to be confused with REST API. So all of these are APIs, and indeed, this is a facade. So our system, which is that inner hexagon, it is very big in terms of amount of code. It's got lots and lots and lots of business logic. But we don't want all of these, REST API, SOAP API to have to think too much. So by exposing the ports, we are exposing just the surface of something. It's very thin. It is a facade. So we can say that this is, a facade. Well, these are also facades, except they are HTTP facades. This is not a HTTP facade, so that's one difference. And you can also think of the port. Imagine if your inner hexagon is like the internal part of Earth, and these driver ports are like the crust of the Earth, like what is being exposed to the external world. Okay, I'm not sure if that analogy is good or bad, but I think we can stick with the word, facade or user-side API. So let's see. This was all the time I talked about just one user-side port. But as we've mentioned before, in a more general sense, we can have more ports, so not just one. And here I'm going to give an example of another port. Suppose we have some pricing service port, and this pricing service interface is essentially, it has, well, just let's say one method, and it's called, sync prices. And we have an adapter, a job scheduler, which calls the pricing, service to do sync, let's say, to sync all prices. And maybe we also have a RabbitMQ consumer, which calls this interface and calls the method, sync price for specific product, assuming that here we got some event that a certain product was updated. and we need to perform sync. So I just wanted to illustrate this, the fact that we have we can have multiple ports, and that each port could have multiple adapters. So that's essentially the main story behind all of this. Can we remove all dependencies as in chip design? Maybe I would need further clarification to that question. So currently the only dependencies that we have is between the adapters and the ports, but I would need further clarification. So it can be called application public services. So yeah, this whole thing, this yellow stuff is what in hexagonal architecture is called the application. And we could say that these are like the public services, whereas everything else is internal. So yes, we could say like that. What is the benefit to have an interface service with one implementation? That's the part, this similar question was raised also last time. So I'll give a recap of the response. At first, it looks redundant. Why would we do this? But the part where it is useful is when we want to do integration testing for the REST API adapter, or the SOAP API adapter. We don't want to test the real business logic as well. We're only interested in the adapter and the port and nothing else, and not the real business logic. If this interface did not exist, but instead, if we directly connected to the order service implementation, then by executing that test, we would be traversing the real business logic itself. I will leave it as a question to the audience if anyone can explain what are the problems of having that mixing. So I'll leave it as a thinking question, since that topic was brought up last time, and I can see that maybe many people are interested in this. So exactly, the ports are exposed, and on the driver side they should be used, and in driven side they should be implemented, and the rest of SOAP is a driven side as a client developer point of view. So okay, great. Yes, on the driver side they are used, whereas on the driven side they are implemented. The part about REST or SOAP, here the REST API and SOAP that we have, they are on the driver side, but we will also see on the other side that we could also have REST and SOAP when we're connecting to other REST or SOAP services. Doesn't this have too much responsibility? So I'm not sure which comment that was related to. Feel free to clarify. Okay, continuing on. I'm now going to move onto the fact that we have implementations. So here was an order service interface which had methods: submit order, cancel order, view order details. The order service, this was an interface, whereas this is some class. So we have an order service impl class which implements this interface, and in those methods it's actually doing stuff. So for example, in the method submit order, it is doing order equals new order, fill in the details with the order items, pricing, do some calculation, and then say repository interface, can you save this order? So this is the part that actually has code. And the other port, the pricing service interface, it also has its implementation, and we can see there is just one implementation. Let's now move on to the driven side. So this order service implementation to do stuff, it has some dependency on the external world. So the order service implementation needs to save the orders in some kind of persistence mechanism. But from a business logic perspective, we don't care about which database we're using. I mean, we just see it as some kind of IO. You know, let's imagine if persistence storage is just some box and we put some orders inside, you know, like adding an order, updating an order, or we can retrieve orders from that box storage, for example, you know, get order by ID. So we introduce some order repository interface which abstracts away the storage mechanisms. So it would have methods like add order, update order, get order, delete order by ID. It has typical CRUD-like stuff. And look at the possible implementations. So we could have a fake implementation of the order repository. We could have an implementation for SQL databases, maybe using an ORM, like Hibernate or Entity Framework, or maybe using some light ORM, like, for example, Dapper, or anything where you're writing the raw SQL queries. Maybe we could use some NoSQL database, maybe MongoDB, Redis, Cassandra, Neo4j. Maybe we're not going to use databases at all, but we're using some file storage, maybe the local file storage or Amazon S3 or Azure Blob Storage. All of these are simply implementing this interface. And due to this dependency inversion, this order service implementation does not have any knowledge about the existence of these implementations. All it knows is that there is an order repository interface with methods add order, update order, delete order, get order by ID, and it does not care what the underlying storage mechanism is. So this is a really crucial concept. Okay, let me see. Coming back to the chat, since there are a lot of questions. So doesn't this have too much responsibility? And the clarification was the yellow. The yellow is indeed the part where we want most of our code and most of the complexity to reside. So indeed, most of the responsibility, most of the work will be on the yellow. So that's the actual hexagon. Okay. What is the scope of the yellow application domain? Correct. So it's essentially the application we could say layer of the whole system here. We could split it into application services, domain entities, or maybe we're not going to use domain-driven design and just have everything within these application services. That's also a possibility. So that's yet another question which I might put on a to-do, which is also related to layering, the fact that, you know, what is inside, for example, application services or application services and domain, or use cases and domain. This is also not specified by hexagonal architecture, so it gives you freedom. We can discuss that part as well. Okay, many of time you don't need all implementation in the same service, but you can create a factory to put all different service implementation in the same place. Maybe it would be useful if you could provide additional information about this part. This comment does look interesting. Where you put the implementation, okay, I just want to emphasize here. Just because I created here this order service implementation class. It could be a big class, or it could delegate to some other smaller classes. So maybe it won't be fat. Maybe it's going to delegate to some other classes, so that we achieve, single responsibility principle. So maybe it's going to be like this. We're going to be creating, it's doing too much. So this thing will still exist, but we don't want it to have too much responsibility all on its own. We're going to delegate some responsibilities. So then this serves just for purpose of implementing the interface, but then it delegates onwards. And whether you use some design patterns, factories, whatever, single responsibility principle, up to you. It is not defined or enforced by the hexagonal architecture itself. The yellow block is your core. It has your domain and its business logic. That's correct. So this yellow, we say it's the application. This is where we're modeling the domain. This is where our business logic is. Okay, with Java JUnit, it is possible to mock concrete classes. Okay, I like this. This is a counter argument compared to the previous statement, which was that question, why have why have an interface when there's one implementation? And then when I said the response, well, when we want to test the adapters in isolation, we want to be able to mock it. So it's good practice to have interfaces when mocking. Now, from a technical perspective, it is possible to mock concrete classes instead of interface, which is generally seen as not a good practice. So it's generally preferable to mock interfaces rather than concrete classes. But this is where we raise the other additional point. It's not just about the testing, it's also about the decoupling. So if my REST API had access to order service implementation class, it could happen that maybe here within the order service implementation class, I accidentally or intentionally have additional public methods than what is needed actually by the interface, giving the bad freedom to this REST API to call something that I didn't intend to call. And also, depending on the programming language, if I start exposing this, the compiler may force me to expose other internal types as well. But that one is language specific. So I'm saying if we eliminate this, that we could be getting into other problems as well, because we then start exposing the internals of our system to the external world, like the REST API, and we could give it too much freedom. We could give it possibility to call other public methods here, which was not intended, which would not be possible via the interface. So to summarize, it would be both bad practice in terms of testing to mock concrete classes. We should mock interfaces, and we want to restrict freedom. So with these interfaces, it's very clear restriction of freedom, what this REST API can do. If we give it access to this, well, it could have additional freedom, which is generally has negative side effects. Okay. Yes, that's correct. This whole yellow block, the hexagon, like the core, this is where or the key responsibility resides. Now, once again, to emphasize, it does not mean that we're going to have two huge classes here of 1,000 lines of code. Instead, if this does become thousands of lines of code, we're not going to have it in one class, but where we will be creating various other internal classes and applying single responsibility principle to solve that. Would internal application to application communication also go via the API, or would they integrate directly? So when we say application to application communication, I assume that, let's say in the case of microservices, the other application might communicate via the REST API. So that's one example. Or even if you don't have microservices, but instead have a modular monolith, whereby each of these is like a module, then we still want them to communicate via the ports only and not access the internals. So this yellow stuff, like the core, we don't want anyone accessing it internally, but accessing only through the ports. It doesn't need to have all of these order service and price service in the same place. So let's see, I mean, these services are currently, with this modeling, they are in this application because I wanted to illustrate the possibility of using two ports. You could make an argument, is this too much for one application? Should this have been two applications with one port each? And that whole is another discussion about how we're doing bounded contexts and stuff like that, how we're splitting. In most cases, hexagonal architecture will give you structure and consistency over premature abstraction. You are not going to have different implementation of interfaces. So yeah, typically in practice, we're going to have one implementation for this interface. And even here, in reality, you're not going to start a project with 8 databases or 10 databases. You're going to pretty much be starting with fake and one real implementation. As already said, in many cases, having an interface for just one implementation does not make sense, but for testing purposes. Once again, this can be overcome, at least in Java JUnit. Okay, so I think this is related to the previous discussion. Technically, you could mock out a concrete class, even though it is not seen as good practice to mock a concrete class, but rather mocking interfaces instead. And we also mentioned the second problem, not just testing, but exposure. When you expose an interface, you control what is exposed. It is only that interface, and in that interface, you can clearly see the public methods. If instead you expose this class, you lose control, so you could be exposing much more than with the interface, and then it causes additional higher coupling. It's like, let's think about these interfaces as, doors and windows to the house. We're controlling entry, as opposed to just, we could break down, and not have any doors and windows and just give everyone access to our entire house. But that could leads to additional coupling and problems. So it wasn't just, not only for testing. Would be polyglot for code and data. Okay. That's the problem. Lots of tightly coupled systems were designed to have just one implementation. Then it grows as spaghetti when a second implementation comes. So yeah, I mean, these problems could occur as well. So that's why interfaces, we could say, they give us additional conceptual benefit. It really forces us to think about what are we exposing without thinking about the implementation. Okay. So let's see, we have the order repository interface. Then maybe in some of these methods, like when we have that method submit order, we also need to send a message that an order was created, because some other systems somewhere else need to know that an order was created, and maybe they need to send SMS messages, email confirmations. Maybe they want to add this person to their marketing newsletter because they made an order. We don't care. All that this needs to know is that there exists some order notifier interface, which with a method like notify and accepts an order. It could be implemented with RabbitMQ, it could be implemented with Kafka. We don't care. And also, okay, for unit testing, we could have, fake or mock. Maybe we also need, when we submit order, that we process the payment. So we want to say, payment gateway interface. Could you process payment for a certain order ID? And we don't care about what payment gateway we're dealing with, and maybe just to have competitive advantage, we want to support multiple payment gateways simultaneously, like PayPal and Stripe. Maybe we also need to do some shipping. So after the method, for example, create a submit order when it executes, and at the end we want to say shipping gateway dot start shipment or something else. And we could be connecting to maybe some well-known APIs to do the shipping, like DHL. They have their public APIs. But maybe we're working with a very small shipping company, and that shipping company doesn't even have the API, but they said they will develop it for us. So look at this, we have an interface, and here this API, so this adapter doesn't even exist yet because it's being developed by another company, another team, and we are not blocked anywhere. So we've seen here that we can have multiple adapter implementations, and that even if we don't have an adapter implementation, that we're actually still not blocked in development. Then the other topics that, okay, everything that we've seen above, it was about I/O. So databases are I/O. Messaging is again some kind of I/O. These payment gateways, the fact that we're calling some other REST APIs or calling some SOAP services, this is also I/O over the network. Okay, this for shipping was also some I/O. We're calling some REST APIs or SOAP services, etc. But imagine if we also have some randomness here. For example, in the method submit order, we need to generate the order number, and the order number could start with some country prefix, and then it has an auto-generated integer or auto-generated UUID, or maybe some other special definition of random generation. Remember how we said that we're going to have tests, unit tests, targeting the port? Okay, we've abstracted away the I/O, but the other thing that also needs to be abstracted away is any source of non-determinism. So anything that's random, we need to abstract it away for purposes of unit testability. That is why we introduce here an order ID generator interface, which has a method like next order ID, and it will give us back some random string or integer or whatever else. And adapters could do the random number generation, and we're using some third-party libraries here. Another source of also non-determinism is time. So suppose that we have logic that within submit order, that if it's Monday or Tuesday, the order price will be calculated with some special Monday or Tuesday discount. So that's an example of depending on day. Or there could be dependency on time. For example, if you submit the order between 9 and 5, our system will accept your order. But if you submit your order after 5 p.m., then our system will return an error. So to the caller. So that's an example of having business logic which is dependent on time. In the same way that random numbers are non-deterministic, time is also non-deterministic. So this is why we abstract away time for purposes of unit testability of business logic. So to unit test this order service implementation, well, I mean, unit testing the order service interface, which is initialized by constructing the order service implementation. To unit test that, we have to abstract away non-determinism. And we're nearly towards the end of this diagram. Let's see, we have this pricing service implementation. Again, similar story. This pricing service implementation, maybe it needs some source. Where is it getting the products from? In reality, it's some other external microservice, or maybe an Excel file or anything else. So this is abstracting away over I/O. And this pricing product service, after it gets all the products, it wants to sync the new product prices into our product repository. So it's going to say, product repository.update product. And behind this, we have some, let's say SQL database implementation. And you'll also notice that some of these driven ports could be used by multiple of these services. So for example, the product repository interface, it's called both by the order service implementation, and it's also called by the pricing service implementation. Okay, so this is the end of this diagram that I showed here. I will have a look at chat, and then we can also get to these questions that were raised here as well. So let's see. Where we got up to. So the domain should not have multiple implementations, ways to do the job, only one way to do things. So this indeed is the typical thing. So when we have the order service interface, we have just one thing, order service implementation. We would typically not have a second order service implementation. This is the case in essentially 99.99% of cases. Now there could be cases like, suppose that we're developing this system for a global audience. So maybe depending on different countries, certain parts of this may have multiple implementations. So let's say, suppose that the order price calculation could differ based on different countries. So that maybe we want to use our strategy design pattern or something. So we could have possible variations here, that we could use, some design patterns which cause multiple implementations. But just to emphasize again, there is one implementation of this thing. But here, in terms of the internals, if you choose to use design patterns which cause multiple implementations of things, such as multiple implementations of pricing calculations, sure you could. But for this thing, it's just one implementation. Can this scale to be massively parallel. So the topics of scalability and parallelization, I would say, is independent of hexagonal architecture. So we could not use hexagonal architecture at all, but still have a scalable application. Depending on third-party libraries is a security concern. So with these third-party libraries, such as, let's say, random number generation, we could depend on it, or we could implement the algorithm ourselves. Okay, even if we implement it ourselves, it would still be in the adapters. Or even here, we are using some third-party gateways, whether we choose it or maybe another team in our company is going to implement it. It remains a choice. Okay, so now going on to these topics regarding architecture and layering. So this is where maybe I'm going to start a next drawing, and most of these questions are now concerned specifically with this yellow stuff, so that inner hexagon. So I'll just mark it yellow here. So that's what we're talking about. And the fact that we have these ports. So I'm just going to take the 2 ports that we have. And let's see how this could be done with different architectures. And I'm just going to copy paste just a few of these ones. Just that we have a few ports, but I'm not going to copy paste all the ports because there are so many of them. And let's look at different architectural approaches. I'm not sure, is this readable? I hope it is. So let's start with the simplest approach, the big ball of mud approach, which I'm sure is famous and well known to people. Oh, okay. And we're now, I guess, going to answer all of those interesting questions that happened regarding these implementations. So of the ports, so I'm going to copy paste that here, and let's draw the dependencies again. So this dependent here, or the ID generator, this one also products, this one products. Okay. So let's start with just the big ball of mud approach. I would say that if all that we have and is just these 2 implementation classes, and this could like grow to thousands and thousands of lines of code. So even though there's just a few, methods that we're implementing, but the logic could be really complex inside. And I've just have these 2 classes, and they would grow to thousands and thousands of lines of code, and this would become unmaintainable. So this is, for example, structuring with the big ball of mud approach. We could also have some kind of, clean design internally, so not big ball of mud. We don't want this to be too thick in terms of code. Instead, we want to create some other helper classes, but we split responsibilities. So notice how it was like really a big square. So instead of having a big class with thousands of lines of code, let's split it up in some logical way into multiple classes, each of them, having different responsibilities, and well, okay, sorry, I'll just put it here. And this service implementation could, delegate to them. Maybe some of them, maybe this one then calls another class. Maybe this one calls this class. Okay. So this is already an improvement that we have, some kind of applying, for example, solid principles within our design. Both of these ones are hexagonal architecture. Like the hexagonal architecture does not prescribe what's inside. So this is valid, and I'm just going to copy paste. Okay, so all of these are some internal classes. Well, internal classes, or it could be internal interfaces. Oh, that's the other part that we need to distinguish, interfaces. So when we say ports, port is not every interface that exists. It is only these publicly exposed interfaces here. For orders, maybe we have different pricing strategies. So maybe we have interfaces here, like some pricing strategy interface. So I just want to emphasize that this stuff inside are essentially internal classes and any internal interfaces. Okay, at least now our design is better. Let's think about maybe we want to apply domain-driven design. So with domain-driven design, let's see, we would have let me see, domain-driven design. This in domain-driven design is called the application service. So these are two application services. And we could come up with some domain entities. Sorry. So we could have some order entity. We could have a product entity. And this order entity inside itself, it would have methods, to calculate the order price. And so we have application services, and they are dependent on some entities. Well, not just domain entities, but they could also be domain services. Maybe I'm going to have some pricing domain service. This is, it's an entity. So and let's see. Okay, so this is an example of domain-driven design, which is where we have application services plus domain entities, value objects, domain services. So it's essentially two layers, like one is the application layer and one is the domain layer. So I'm just going to illustrate with just a different color the fact that this now is the domain layer stuff. Okay, let's move send to back and this send to back. Okay, so here we have a split between application layer, and here we have the domain layer. And this actually fits in with clean architecture. What I've drawn here is pretty much how clean, I will go to clean architecture next time, but if you have a look at onion architecture, I would say it corresponds to onion architecture. And let's see what else remained from those questions. Okay, you could say that we don't like the fact that we have multiple methods per this interface, that you want more granular ports. So we could say that instead of having an order service, so here we had an order service interface, and it had methods submit order, cancel order, get order details. Maybe we don't like it that way. Maybe we want more fine-grained ports, which are, for example, submit order interface, cancel order interface. And for this one, for pricing sync interface. And I forgot one more, get order details interface. This is actually essentially what I'm drawing here. It will end up as clean architecture. So if I have the interfaces like that, and then most likely when I structure my implementation, I'm going to have a submit order implementation. I'm going to have cancel order implementation. I'm going to have get order, and I think with this diagram we will be finishing up. So after I finish this one, so cancel order, and we could have get order implementation. So it's the same thing as above, it's just that now our interfaces have become more granular. Each of these interfaces has just one method, handle or execute. And let me see. Okay, I need more space here. And okay, and these ones, okay, so cancel order, so it could depend on the order entity, for example. This one might also. So there we go. Now our application layer consists of the use cases, and we still have the main layer, and everything else stays pretty much the same as before. So this is called essentially clean architecture, whereby our ports are granular. So in clean architecture, we have the application layer, which consists of the use cases, plus the domain layer, which is entities, etc. I mean, like value objects, etc. And these ones we would most likely call it, for example, submit order use case, cancel order use case. So instead of service, we call it use case, but it's the same thing as a service. It's just more granular. Use case, use case, use case. So there we go. All of these ones satisfy hexagonal architecture, but we've seen that the actual structure inside is completely different. So the internal architecture, as in what layers and even what layers we're going to have, is essentially our own choice. It is not prescribed by hexagonal architecture itself. So, okay, I thought that was quite a lot of stuff. Let's see What is the difference between pricing domain service and pricing service implementation? Okay, I just realized that I'm using the same name, which could have led to confusion. I'm going to be maybe just clarifying that this was about product pricing, whereas this one was about order pricing calculation or order pricing domain service. So, and maybe here also product pricing sync. So they are essentially two separate things. The product pricing is concerned with this is concerned with syncing the pricing of our products, whereas this one is concerned with some, let's say, domain logic that due to different countries that we're calculating price in a different way. Maybe I'll call it the price calculator, just to distinguish it further. So very nice, the last diagram with clean architecture. So yeah, thanks for that. I mean, and this we can, it also corresponds to historical evolution. So hexagonal architecture itself is the foundation. And then historically there came along onion architecture, which essentially, and domain-driven design, which introduced this possibility about application layer and domain layer, and they typically had these application services, whereas the main unique contribution from Uncle Bob in clean architecture was the fact that he took these application services, made them more, I would say, granular in terms of exposing the use cases, so that here we can already see the use cases at a glance. Okay, so that is all for today. I hope that you enjoyed it. I will be looking, I guess, during the next session, following on with these other questions that we didn't answer, and also other popular questions that came along, such as databases, is it all interchangeable or not, and also points like authentication and authorization. So let's see how it goes. And the other part that I also forgot to mention is that actually our next immediate upcoming session will be a live coding session. So up to now all of this was conceptual with diagrams, but in our next session we're planning some live coding to actually show this transformation in practice. And let's see also a few more other points. Maybe the first diagram is a transaction script implementation. Yes, we can call it that way, but it is transaction script. And what do you think about one feature per use case interface? E.g. create order, add line, order, cancel order. So yes, here when it's split in this granular way, there literally is only a single implementation. So I want to say that submit order use case interface, and maybe I will separate the words just so the formatting here looks better. It would have one method. It will return, for example, submit order response, and the method could be called handle or execute, and it accepts some request. So this is just, it is one method only. Even our next interface, cancel order use case interface, it has, for example, cancel order response, cancel order request, and it's just a single method handle. So unlike the case above, where one service, application service, typically contains multiple methods, here, when we go this granular way, each use case has just one method executing that use case only. Which language? So the upcoming one will be in TypeScript, but in the future, depending on any other interests, we could have it in any other languages as well. But that one, it will be recognizable to anyone who is also a Java or .NET developer, which also happens to be my main background. So just to emphasize, that upcoming live programming session is useful to whoever is, I would say, backend developer, regardless of the programming language. So yeah, I'm looking forward to you joining the next live coding session, and then in the future after that one, I also do plan to continue on with the theory, like these other questions that we still have open. So I want to say thanks again, everyone. I hope that you enjoyed this session today. Feel free to like and subscribe if you found this useful, and I look forward to our upcoming sessions. So thanks again, and I wish you all the best. And here is just, as I said, the remaining links, and also feel free to connect or with me or follow me on LinkedIn, Twitter, GitHub, Instagram, and also here on YouTube. So thanks again, everyone.